I'm sure that all of us at some point have done this particular experiment that you see there me doing, where you take a straw and then you put it in a liquid. It doesn't matter what kind of a liquid. Most of the time it's some kind of a water liquid. Now, and if you do that, and you put the straw in and you close it on top, and you lift it up, so as you can see there, the water doesn't seem to flow down. And as you know, gravity is constantly acting on pretty much any object near the Earth's surface. So why isn't this water flowing out? Well, it's actually to do with pressure, and there are certainly forces that are present if you have pressure. And if you start to understand how fluids work and how pressure works within fluids, then you can explain this phenomenon to anybody. Now, most of the time in these videos, people will say, well, the atmospheric pressure at the bottom that we have is basically greater than the actual pressure that we have, which is coming just from the fluid itself. So therefore, we have some pressure, so P atmospheric, which is pushing this up, and the actual pressure, okay, or the force which is caused by the actual fluid is not big enough to overcome the pressure at the bottom. And that is true. That's exactly what's happening. But now let's try to break it down and try to utilize our understanding of physics in general. All right. So here it is. If we have a straw, so if you take a straw and you try to fill it up, so you put it in a container, let's say that this is your straw that you have. Now, towards the bottom, okay, there, so within here, so we have, let me do it maybe like this, here is the actual fluid. So now for the sake for us, let the fluid just be water. Now, water has a certain density. So this density is basically 1,000, kilograms per meters cubed. Now, give or take, this is typically at a certain temperature, but it's a very good approximation for us. So that's the density of the fluid that we might have. Now, if you have the top of the straw, which is open, then what's going to happen is that you're going to have this pressure. So that pressure, P atmospheric, is going to be pushing down. I'm going to write this out in here. So this is going to push down like so if it's open. And then, yes, you have the atmospheric pressure, which is also, pushing this up. So this is normal. Because the distance between them is not that far, these are basically canceling each other off. This is going to be just a few centimeters away. Now, if you know in fluids, the deeper that you go, the more pressure that is exerted. So this is the same thing that happens in air. The deeper that you go, the more it is. But because the straw is not very big, so the difference between the pressure on top, so this one, and the pressure at the bottom is not that big. Now, technically, what's going to happen, the pressure at the bottom right here, so I'm going to put B, is going to be ever so slightly, okay, bigger than the pressure on top of the atmosphere, okay, at point A. Let this be point A, and this be point B. But it's minuscule. So basically, these are approximately the same. Now, because these are the same, then what will happen is if you don't have your finger right on top, then this pressure, or these two pressures, cancel each other off, right? Because they're in the opposite directions in here. So you can think about forces and vectors. So if they're in opposite direction and in the same magnitude, then they cancel and the net force is zero. So the only force that you have present is with regards to the actual fluid, so the liquid inside of there, which is going to be the water. And then that means that the gravity, right, so we have an extra force, okay, coming in from gravity on this liquid, and it's going to flow this right out. And that's exactly what you would see there. So this indeed is what's going to happen. So if you take the straw, right, so if you have it, I don't know if you can see it right there, so let me just kind of do it like this. So you can see it right there. If I let it go, it falls down. So no mystery there, right? It kind of makes sense. Okay, gravity, okay, is pulling this down, okay, as it falls through. So that's fine. But as long as I hold the actual straw, okay, what's happening? Why isn't the fluid, falling down? Of course, I have to kind of really tightly hold it. If it's not super tight, some air might go in and you might see a drop falling or something. But if you really tighten it up, nothing is going to fall out. So now the question very often is from people, what is happening? Why isn't gravity pulling this down? So, well, what happens is, in this case, well, if you close this down, so let's say if you put your finger on this, then, you're going to be cutting off the pressure from the atmosphere. So it's not going to get in there. Now, of course, you still have air in here. So you still do have air inside. And there is some pressure from the air which is pushing this down, but it is not the atmospheric pressure anymore, because you only have a very little amount of air and it's not open to the entire atmosphere going all the way, about 100 kilometers up, okay, or about 120 kilometers up. So you only have a very minuscule amount. So you really just have this height, okay, of the air. So if you wanted to know what that pressure from this air inside here is, well, so that's nothing extraordinary. This goes back to the pressure in fluids. And for that, okay, at a particular depth, I can put up a link up above there. And that particular pressure is just simply the density of the air that we have multiplied by the gravity times the h, and the h would be the height. Now, in this case, if it's a straw, the h is tiny, right? So this h is, maybe, I don't know, 15 centimeters, give or take. I think I measured it when I was doing the experiment here. So this is just nothing else but 0.5 meters. So it's minuscule. This is just 9.8. This is what you have there. This is meters per second squared. And the density of the air at approximately 1 atmosphere is, 1.204, kilograms per meter cubed. So if you multiply these 1, 2, and 3, well, you're going to get almost nothing, right? So there's no pressure coming in from there. So what you have is 1.204 times 9.8, times, let's say, 15, which is the height. Let's round that, okay? So let's, it's 1.769. Let's just say that it's 2 pascals, all right? So that is the pressure. I mean, that's nothing in comparison to what the pressure at the bottom is. So the pressure over here, okay, so that we have, this pressure hasn't changed, because when you lift the straw out, that pressure is still present there from the atmosphere. But pressure of the atmosphere at 1 atmospheric, so this is 101.325 pascals. So as you can see here, this pressure, okay, which is pushing this down, right? So you have that pressure there. This pressure is way more, it's 101,000 that you have. So clearly this one right here is really negligible. And that's what we typically assume, that the air, okay, would be negligible inside, okay, once you close it down in any way. So really the other, pressure that's coming in is from the liquid. So you might say, well, okay, but then what is the actual liquid? So within here, right? So this liquid that I have, and I put a dye on it, it's kind of a little bit of pinkish dye that you see there, right? So, that's my kind of liquidy, kind of pinkish dye that you see. So that liquid, how much pressure is coming from that? And, so within here, within the straw. So this height, okay, so from here to here, I think I measured it. It was about, 6 centimeters. So 6 centimeters is 0.06 meters, right? So if you want to find the pressure inside, which is coming at that depth, so we know the pressure on top, right? That's the air pressure. It's only 2 pascals. And then the pressure from the entire liquid in the straw, so that would be the pressure. Okay, this is from the actual liquid. So I'm going to put liquid in here. That's equal to the density, right, that we have, times G, again, times the height. Now the density in this case, well, that liquid, it's mostly water. So that's going to be about 1,000, times 9.8. And then this times the actual height, let's say 0.06. So again, we can certainly plug this in. Now the 1,000, I might say, ooh, maybe it's going to be a lot, because 1,000 times 9.8, all right, that's, we're getting up there, right? And then we can take this and then multiply it now by only the height, and that shrinks it down. So it's 588, let's say about 600 pascals if I round this. So really, the total pressure that you have at the straw is coming from the air inside plus the liquid, right? So that's the total pressure that you have on the inside. That pressure is just 2 pascals from the air, and then, approximately 600 pascals pushing it down. So that's not going to overcome this pressure of the atmosphere. And that's why when you close it, right, that pressure at the bottom is just so much greater. Now, a very good question is that, hold on a second, if the pressure at the bottom is so big from the atmosphere and the pressure from this liquid in the air is not, why isn't this pushing the liquid actually upwards, right? And we see that if you take a straw and you start sucking out on it, so basically you do negative pressure, so it's like you're sucking it up, you notice the liquid goes upwards because the pressure is pushing it down, right, up above, so it's pushing it, and then you're adding extra pressure, negative pressure, so that the liquid goes up. But if you're just holding it, it doesn't seem to go up, yet the pressure is so much greater. If you were just thinking about forces and you were saying that, oh, if the force up, even if the force up is, let's say, 2 newtons, and the force down right here, even if it was only 1 newton, there's still a net force up of 1 newton upwards. And what happens with forces in that way? Well, this is going to accelerate, and it's going to accelerate upwards if that's the net force. So something else must still be acting that the liquid does not go up even though the pressure's there, at least when we hold the finger. And the answer is that in this straw, what actually happens is the liquid itself, right? So there's walls, this is a solid. So there is adhesion forces between the water and the actual straw itself. It's adhering to the walls. And then there's cohesion forces within the water that's keeping them tight together. So it's almost like saying that there is frictional forces that the pressure pushing up still has to overcome. And it cannot overcome those actual forces. Now, of course, if you start sucking up or you start adding more negative pressure in there, it's going to start to rise up. But it has to overcome those adhesion and cohesion forces. And if it will not, that's the same thing as any item. If you put and you have a ramp, right? So if you have a ramp down and you know that if you put something on this ramp down, right, it's not going to necessarily start to slide because there's friction forces, force of friction, although this might be caused by the force of gravity. Now gravity is going to be this way, so it's going to be that particular component. So that's force of gravity is going to try to pull it down. And however, the force of friction is preventing it. This is exactly what's happening here. You do have that pressure, the forces that are pushing it up, but the adhesion, cohesion forces are preventing this liquid to still go up. So that's why it just stays there, right? But as soon as you let it go, okay, now all of a sudden the gravity takes over, breaks down those adhesion and cohesion forces as well. They're very minuscule in comparison, okay, as soon as you let go, because you have that pressure from the atmosphere up, pressure down, those cancel off, and then the only thing that happens is that you're only allowing the gravity to work, and then it starts to fall down. So there you go. That's how this straw works, and you've seen now some numbers to be able to back up, which typically you may not be able to see probably in some other videos. So this is much more detailed. And this is really for, students that are actually taking physics. They're interested in understanding pressure within fluids. So that would be gases, liquids, plasmas. Okay, so this is a very nice, good experiment and something that you should be able to understand once you understand how to calculate all of these pressures and then what's happening. All right, thanks for watching. See you in a future video. Bye, everybody. Happy learning.